Last time we talked about scalability, and we argued that scalability really means working in parallel. And we talked about this specific task, which is, read trimming. Okay, so this is a bunch of small genetic sequences, and your task was to trim off the last few characters from each one. Okay, and we sort of showed that this is pretty simple to think about in parallel. You would divide the set of reads into chunks and put them all on separate computers and process them all in parallel. Here, there's a function f that takes a single read and trims off the last few characters and returns the prefix. And you can apply this function in parallel, and you can get out the data set you want, which is a set of trimmed reads. Okay, so let's see some more examples. So a new task that was actually needed to be performed at the New York Times in 2008, and they have a couple of blog posts about it that you can read, was, in a simplified version, was to convert a bunch of TIFF images into a different format. And what was really going on here is that they had digitized images from the newspaper along with some information about the optical character recognition, so some extracted text, and they wanted to turn this into a more web-friendly format. And so they had to convert the images to a web-friendly format, and they also had to convert the extracted text into a little package of JavaScript code. Okay, so they're going to get ready to put this stuff on the web. All right, so this is 405,000 images, which was quite a bit, especially at the time. Okay. But the schematic looks sort of similar, right? You take a big set of TIFF images and you split them into chunks and put them on a bunch of different computers, and you have a function f that converts a TIFF to a PNG and does the other work too, let's say. And what you get out is the data set you want, a bunch of PNG images. Okay, and they're distributed across these machines. Fine. So let's look at another example. All right, so now we want to run thousands of little simulations. And what we have are the parameters to each one of those thousands of simulations. And so an example of this at the URL here at the bottom of the slide is from simulating muscle dynamics. And this comes up a lot. You have these Monte Carlo simulations that need to do, they understand sort of phenomenon stochastically by running lots and lots and lots of simulations with different kinds of different inputs and then kind of averaging the results, okay, as opposed to modeling everything precisely. So now you want to run thousands of simulations. Well, you have a set of inputs, of parameters to these simulations, and you break them into chunks and put them all on separate machines and apply the function. And here the function is actually running the simulation. And what you get out is the output of the simulation distributed across all of the machines. Okay, so there's, a pattern should be emerging here, right? So another example. So imagine each one of these little bars is a document, and your task is just to find the most common word in every individual document. Okay, well, same thing, distribute the documents across the K computers, and then your function f now in this case opens up a single document, figures out which word is the most common in that document, right, and just produces that word. And so now you have a big distributed list of pairs where, the first part of the pair is the document ID and the second one is the word. Okay, so that could be useful, but it's a bit contrived. Consider a slightly more general program that computes the word frequency of every word still in a single document, right? So instead of just finding the most common one and producing that, now you're going to produce a histogram of the frequencies of every word in the document. Okay, so given this input, you produce all of these items, right? A set of items. And the only reason I'm making this distinction from the last one is that the last one, took a single document and produced a single word. Now we're taking a single. Just want to make it clear that that's allowed. Okay. Oops, the animation isn't here, but I don't think I'll bother fixing it. So you have millions of documents. You distribute them again. Now your function returns a set of word frequency pairs, right? But that's okay. And now we have, lots of little lines here, each line representing a single word, let's say. So they're not one-to-one anymore. But that's no problem. The function just returns a set of things. All right. So fine. So there should be a pattern here, right? We have a function that maps a read to a trim read. We have a function that maps a TIFF image to a PNG image. A function that maps a set of parameters to the simulation result, right? It's the simulation itself. We have a function that maps a document to its most common word. And we have a function that maps a document to the histogram of its word frequencies. Okay, so good. So these kinds of tasks we think we know how to do in parallel. Given a big set of objects and a function that knows how to process a single object, you should be able to think about how to parallelize this, right? I'm giving you a treat, but we can abstractly understand how this is done, right? So let's say that one more time. We have a big set of objects with a function that maps a single object pile of computers, right? The objects among the computers and the function f in parallel. This is trivial. All right. Okay, so what if we want to compute the word frequency across all documents, not just a set of frequencies for each document, or the frequencies for a single document? Okay, so here, if we have these three documents, now we want to get a single histogram that counts up the number of times the word people appears across all three of them, and the number of times the word government appears across all three of them, and so on. So let's go back to our schematic here, the pattern. Well, now we want to compute the word frequency across 5 million documents, and we can still distribute them among k computers. So far, so good. And then for each document, we return a set of word frequency pairs, and now I've switched the notation here from F to map, since we can consider this a map. That's the terminology I used. Okay, but now what do we do? Right, so what we could get out here, what we will get out here is a set of frequencies, but that's not what we want. We want a one big histogram. And to build this one big histogram, we have to make sure that a single computer has access to every occurrence of some particular term. So if the word history appears in some document on this machine, and it appears twice in this document and 3 times and two times in documents on that machine, and so on, we have to sort of group those all up and send them to a single place just so we can count them. Okay. So let's look at this again. So if we distribute the documents across these computers, we apply our map function to each document in order to produce a set of word frequency pairs, and now we have a big distributed list of these sets of word frequencies. And now we want to get these workers involved in the process. And these guys are going to be the ones who count the occurrences of a particular word. Okay, and so imagine all these little colored red lines are occurrences of words, such that all the red lines represent a single word, occurrences of a single word, and all the green lines represent a different word, and so on. Well, so these guys are going to get sent to their respective locations, so such that this worker is in charge of handling all the occurrences of the blue word, and this worker is in charge of handling all the occurrences of the red word, and so on. Okay, so now instead of lines that go, from one to one, we have lines that go from this one computer to a bunch of different computers. Okay, and so on, right? So you have to sort of shuffle the data, we have to spray this data out across the network in order to regroup it. Now, fine. So now that we have the data grouped the way we want and partitioned the right way, we can apply another function, which I'll call the reduce function, which in this case it does something very simple. It just counts them. And that allows us to produce our final result, which is, oh, there are 4 green words and 4 red words and 3 blue words, and so on. Okay. So now the schematic looks a little different. We have a sort of a two-step process. So we start with some large set of objects distributed over a bunch of machines, and then we want to apply some function f to each one of those objects, and that was our first step. But then the output of those functions are all going to be redistributed across the network and grouped to form groups. Okay. And then the second step is to process each one of those groups. So I'll write, instead of f, I'll write map here, and I'll write reduce here. Okay. And so that's exactly what MapReduce does, and we'll explain this in more detail next time. But the key idea here is that the user, the programmer, is going to write these two functions, a map function and a reduce function, which are serial. And what I mean by serial is they're not parallel. You don't have to worry about how to manage just
program a distributed cluster within each one of these functions. You just write a function map that takes in an object of some kind and returns some other object. And I'm not using object in this sort of object-oriented sense here. It's just sort of in the mathematical sense, just any sort of input to produce any kind of output. Okay. And then the reduce function takes a set of objects, which I'll note this way, and returns some other kind of object. And actually this can be a set of objects as well. And in fact this can be a set of objects as well. So maybe I'll switch colors here. This can actually be a set of things, and this could actually be a set of things. So for example, we saw a document returning a set of word frequency pairs. But you can think of it, it's not necessarily important to understand what's going on here. Okay, so this is an interesting hypothesis, right? That perhaps all distributed algorithms can be expressed as sequences of these two-step operations, right? A map followed by a reduce, and then maybe more map reduce, map reduce, map reduce as needed. Okay, and we'll talk about that in more detail next time.